Okay, and we're on to the final stretch and the last few questions where I'm allowed to use a calculator now because that would be the intention. Let's calculate the percentage by mass of rhenium in rhenium trichloride. Might take you a little bit of time to find rhenium, but it's here on the periodic table. So basically there's just one of them. So our mass of rhenium is 186.21. The MR of this whole thing is basically, you've got 186.21 plus 3 times 35.45. So that comes to 292.56. Okay, when you add them all together, so that's divided by 292.56 and then times 100. So 186.21 divided by memory recall times 100. So that's 63.648. We put that to percent. I could shorten that to either 63.6 or 63.65. It doesn't really ask for sort of. I suppose that they're 5 sig figs, so really I should probably leave that as 5 sig figs as the answer there. So 63.648. For the next bit then, we've got a 100 centimeters cubed sample of soda water containing 3 times 10 to the minus 2 grams of bicarb or sodium hydrogen carbonate. What's the concentration? Well, let's work out the number of moles first of all. So the number of moles of NaHCO3 is going to be mass divided by relative formula mass. We've got 3 times 10 to the minus 2. And we've got to divide that by the MR. So the MR using our periodic table comes to, was it 22.99 for sodium, plus 1.01 for the hydrogen, plus 12.01 plus 3 times 16. So our MR is 84.01. So 3x 2 minus divided by equal. So that comes to 0.000357 moles. And then concentration then, well, if N equals CV, then C equals N over V. So that's my number of moles, 0.000357 divided by my volume in decimeters cubed. So that would be divided by 0.1. So that's 0.00357 1 and so on moles per decimeter cubed. My least precise data is 2 significant figures, so I suppose I should probably put that to 2 significant figures as well then. So that would be 0.0036 moles per decimeter cubed. Or I could write it as 3.6 if I want. 1, 2, 3 times 10 to the minus 3 moles per decimeter cubed. Okay. Although in reality any of those, will get the mark kind of thing, because the IB is pedantic, but hopefully not that pedantic. Many oxides of silver, blah blah blah, with the formula AgXOY, all of them decompose into elements when heated strongly. So we heated 3.76 grams of silver oxide, and then that mass of silver remained. Determine the empirical formula of this silver oxide. Well, we need to know the mass of the oxygen that's left it. So the mass of oxygen is going to be the mass of the silver oxide, 3.760, minus the mass of the silver left on its own at the end of it. So that comes to 3.76 minus 3.275, which is 0.485 grams. And then we can create our 2 columns, one for silver, one for oxygen, get the M over the AR, relative atomic mass. So that's 3.275 divided by relative atomic mass of silver is 107.87. And then we've got 0.485 grams of oxygen divided by the relative atomic mass of 16, precisely, using our periodic tables. So our mole ratio comes to, divided by 16, so that comes to 0.0303. Let's get the memory. And then 3.275 divided by 107.87 is also 0.0303. Okay, it's 0.0304, but like I say, sort of they're very, very close together, so it's basically a 1-to-1 ratio. If we divide both of them by the smallest number, which is that one, we're going to get 1-to-1. So empirical formula is just AgO. Okay. Suggest why the final mass of solid heated by obtaining that mass of silver might be greater than it should have been, where maybe the reaction wasn't complete. So if we've got this AgO decomposes to give Ag plus half an O2, then basically the reaction hadn't finished. So the reason why it weighs too much is there's still some oxygen attached to the silver. So that would be one reason. So reaction is incomplete. In other words, some AgO remains. So a design improvement would be to ensure that we heat it a bit longer and check the mass again to make sure it hasn't gone down. A technique known as heat to constant mass. So we should heat to constant mass. So if we heat it for another 2 minutes and the mass has gone down, we know that it hadn't finished. And then again, we'd have to heat it a bit longer until eventually we find that the mass no longer changes even after continued heating. And the final page, so we've got sodium peroxide, Na2O2 is formed by the reaction of sodium oxide with oxygen, as shown here. Calculate the percentage yield if sodium peroxide, if 5 grams of sodium oxide produces 5 grams of sodium peroxide. Okay, well let's work out how many moles of sodium oxide we've got. So our number of moles of sodium oxide, this stuff, Na2O, is M over Mr, which is 5. And then the Mr, let's just calculate that up. You've got 2 sodiums, so that's 2 times 22.99, plus that 1 oxygen, 16. So that comes to 61.98. That's the Mr for the Na2O. Don't multiply by the 2 in front. So 5 divided by that is 0.08067 moles. Okay, so sorry, just a minor interruption there a second. So yeah, that's the number of moles. So basically it's a 2-to-2 ratio, it's 1-to-1, so our theoretical yield would be the same number of moles of this stuff, so 0.08067 could make 0.08067 moles of this. So our maximum theoretical yield, so our mass of Na2O2 would be N times Mr, so that would be 0.08067 times, now again, okay, for the sodium peroxide, that's 2 times 22, well, it's basically 61.98 plus another oxygen, so 16, so that's times 77.98, so times that number of moles is 6.29 grams. So that's the maximum amount we could have made. We didn't make that much, we only made 5.5, so our percentage yield is 5.50 divided by the amount that we could have got in theory, times 100. So 5.5 divided by 6.29 times 100 is 87.4%, to 3 significant figures. Okay, so that's our percentage yield. And the last one then, so is where we've got solid copper 2 chloride, absorbs moisture, then we've got an unknown hydrate, we want to find out what X is, and then we've got various masses. So we need to know the mass of the anhydrous copper chloride, and we need to know the mass of the water. So the mass of the anhydrous copper chloride would basically be, so M of CuCl2 is going to be the mass of the crucible plus the anhydrous copper chloride, 17.917. minus the mass of that crucible, 16.221. Work it out in just a second. And the mass of water, we'll also need to know, well, we could make it more long-winded, but it's basically going to be the difference between these two values, because that's the mass of the hydrated copper 2 chloride with the crucible. This is the mass of the anhydrous copper 2 chloride with the crucible. So it'll be basically 18.360 minus 17.917. So let's work those values through. So 17.917 minus 16.221, so that's 1.696 grams, and then 18.36 minus 17.917 is 0.443 grams. And then our two columns, one for the copper chloride and one for the water, M over MR. So we've got 1.696 mass, relative formula mass of copper chloride is 63.55 plus 2 times 35.45, which is 134.45. So that's 1.696 divided by, there we go. So number of moles, mole ratio, that's 0.0126 moles. And then this one here, we've got 0.443 grams of water, divided by the relative formula mass, which is 16 plus 2 times 1.01. So 0.443 divided by 18.02. So that's 0.0246 grams. We round that up. Divide both by the smallest number, so divide by 0.0126. So then that's equal to 1. 0.0246 divided by 0.0126. That's nearest damn it 2. So our value of x is 2, and our formula is CuCl2.2H2O, where x equals 2. And we make that nice and clear and show the formula. Okay, and that's it, done.